Thank you for the invitation. This is the joint work with Osabi Guardella and Klaus Thompson, and an ongoing work with Subhajit Bhattacharjee. I want to talk about the lifting problem in the category of CSI Jabros, dynamical, CSI dynamicals, and also groupoid dynamical systems. Okay, first, I want to explain about it is.
Yeah, maybe it just needs the focus. So like, hang on. Try again. Yep.
Yes. First, I will consider the category of CSI Jabros, and I will briefly explain the lifting problems there. Let A and B be a CSI Jabros, I be a closed ideal of B, and we have a quotient map. And we have this completely positive linear map from A to B mod I. And the lifting problem asks that if we can find a completely positive linear map psi from A to B, making this diagram is commutative. This is the first version of our lifting problem. And here, okay, first I will describe briefly about the importance of this problem. Maybe the importance written back to the Arvison's works on the extensions theory. And the main thing is that if we consider the class of the all extensions of a CSI Jabros by compact operators, then it forms in the group. Maybe I will use. If we extension of A be the all essential extensions of A by compact operators, but then also we can identify the elements here by some completely positive map from A to the Kalkin algebra for some Hilbert space. And then this is a semigroup, but then the question was that when it is a group. And then existence of the inverse for these elements of here that is like the equivalence classes of the such maps is exactly that if there exists a UC is a completely positive lift from A to BH. And it was an open problem for a while. And the first that Arvison tried to prove these lifting problems for the case of the C of X. And he showed the existence of this map psi for such a completely positive map phi. And then he gave the positive answer that the extension of C of X is group. But later, but still there was a question that if A is an arbitrary CSI Jabros, not necessarily commutative. Choi and Jabros solved this lifting problem for nuclear maps when A is a separable CSI Jabros. And in particular, when A is a nuclear, then all the maps, completely positive maps from A are nuclear. And then this gives positive answers with the extension of the A is a group when A is a separable and a nuclear CSI Jabros. Okay, so maybe this is just a brief explanations of the importance of the lifting problem, but now I want to consider this problem in the category of the CSI dynamical system. It means that A and B are CSI Jabros. We have also locally compact second countable group that acts on A and B, and at the moment I will have this diagram that phi from A to B mod I is the equivariant. And then here I want to find a lift psi that also satisfies some type of the equivariant property. But in order, first I want to explain that how to reformulate this formula. But for this, I want to explain some motivations for this. And during this, meanwhile, also I will explain that how we reformulate these problems in the d-statics, and especially what type of the equivariance property we are looking for. And in order to talk about the motivations to look at this problem, I will explain very briefly about the C0x algebras. I will return back again to these algebras in the last part of my talk. If A is a C-star algebra and X be a locally compact Hausdorff space, then a C0x algebra A, we call C0x algebra if there exists a non-degenerate star homomorphism P of A from the C0x to the center of the multiplier algebra of A. But if we have these non-degenerate star homomorphisms, then we can have these form these quotients AX, and then we can view every A belongs to A as a function from X to these collections of the C-star algebras. But this point is that this A can be a Q with a topology, and we can make it an upper semi-continuous C-star bundle. That if we again considers these special sections of this C-star bundle, then we arrive to A. But maybe the interesting. Okay, maybe it's yeah. Maybe I will explain that here a bit. That okay. So now I have A is C0x algebra, and now I have this X. And as you see here, for every X, we have this fiber AX. It has some continuity conditions too. It's not only this bundle of C-star algebras, but with some continuity conditions. But so now we have one C-star algebra here, and for each point, some C-star algebras here. So it's natural to ask that what kind of the properties A and all fibers are sharing together. For example, if we know that all fibers satisfies in a specific property P, then if X satisfies or vice versa. And there were some works in this direction. And in the particular, we were interested, that is the work of the Hirschberg, Roerdam, and Winter, that they shows that if this X has a finite dimensional, and then A absorbs a strongly self-absorbing C-star algebras only if each fiber absorbs the same strongly self-absorbing C-star algebras. Usually from A to go, if A has the properties, then it's easier to conclude that each fiber has, but the main problem is the other direction. Okay. And okay, it is a strongly self-absorbing C-star algebras, as you know, is a very important C-star algebras in the classifications program of simple unit of C-star algebras. And then the equivariant version of the strongly self-absorbing C-star algebras introduced by Szabo, and then also this is a very important notions in the classifications of the group actions and dynamical system. And then with Osopio, we were looking at this equivariant version of the Hirschberg, Roerdam, and Winter. And we wanted to see this if we have a strongly self-absorbing action. And we know that if all the fibers, and also here, also the actions of the G, they have a GCX algebras. In a way that also induces some actions on all fibers. And we know that all fibers absorbs a strongly self-absorbing actions, when we can say that A absorbs that a strongly self-absorbing actions. And for this, we need to reformulate or find another characterizations of the absorptions by actions of the strongest self-absorbing actions, and it leads us to this theorem. And then, in order to obtain this theorem, we need some type of the equivariant lifting theorem. And especially, I may emphasize here that here, in order from A to B, you see that we have finite sets f of t, f of a, f of g, and epsilon. And we find a completely positive contractive map, especially with this property, that satisfies, as you see, that this is some almost, you can say that this is almost equivariant property. And in the non-equivariant setting, this psi obtains by applying the Jabros theorem to the some UCP map. But here, in equivariant case, we really need to obtain some equivariant type of this lifting problem. And also this guides us that what type of the equivariant property we were looking for. Indeed, we did not need to find the equivariant lift. And also, I will explain that it's too much to expect that. Okay, and then by this theorem, we can extend the result of the Hirschberg-Jordan-Winter in the equivariant setting. But also this was our motivations to look at the lifting problem in the equivariant setting. Okay, and
we made the definition of the strongest for the other. What's the day of E in this one?
You remember that in the D, we have some unitaries.
Yeah.
And then these unitaries should behave well with the compact subsets of the G. That they are fixed them in the, they're fixed them some approximately. Yes. Yeah. Yes. This is, yes. And also for when we say that A is the D delta stable, that A is the alpha is a cocycle conjugate with alpha tensor delta. Yes, you just have a definitions of a strongest self-absorbing actions, but for the unitaries, you need to also behave well nicely with respect to the actions. Okay, so the next one. Okay, but this was our formulations of the lifting problem. And then let here GB as second countable locally compact group. And we have this G algebras. And we have a completely positive contractive map, phi, that admits a completely positive linear lift A to B. Then for every epsilon greater than 0, a finite subset f of A, compact subset K of G, there exists a completely positive contractive linear map psi. That first, it's the lift, and the third, we have this equivariance property. But as you see that we do not assume that phi is equivariant. But then we put these conditions that the equivariance behavior of psi is not only related to the this epsilon, but also the behavior of the phi. For example, if phi is equivariant, then this sentence is 0. But this is a stronger statement. Okay. And also, I wanted to say that we just assume that there exists, if phi admits a completely positive linear lift, and at least Jabros theorem says that if phi is nuclear map or A or B are nuclear C star Jabros, then we always have this condition. Okay, but now before going to the proof and explain a bit of the proof, I will just mention about the unital lift. In the Jabros theorem, if A and B are unital C star algebra, we have a unital completely positive linear nuclear map, then phi always admits a unital completely positive linear map. And also now I wanted to really emphasize is that here all the maps are linear. And then, but in the previous theorem, if all A and B and phi are unital, and even phi admits the unital completely positive linear leaf, there is no guarantee that we can find an equivariant, almost equivariant leaf which is unital. Okay, let me explain a bit more here. Here is the conditions that we need that in the case that all of our CSI Jabros and the maps are unital to find a unital lift. And as you will see, that if G is amenable group, then we know that the induced action of G on a state space A has a fixed point. So it's enough that we just take all of these rho n to be this fixed point algebra of the state space of A. And then, so we can see that if G is amenable, then we can find it unital almost equivariant lift. But if G is not amenable, we can find a counterexample. For example, if G is any non-amenable discrete group, that we have also a G algebra, which is unital and nuclear, but satisfies in this condition that you can find the big class of the groups, like every exact group has amenable actions under some locally as a compact host of space, and then you just take A to be the C X algebra. And then to satisfies in this class of the examples. Then if we see with the trivial G action, and then we have this P of A from A plus C to A, and then we just take phi to the identity map. Then if there exists a unital completely positive linear maps which are asymptotically equivariant leaf in the sense of the first theorem, then we can reach these conclusions that the full group CS algebra of G and the reduced one are same. That is a contradiction that with G is a non-amenable. But especially I really wanted to mention this one because we will return to back to these arguments later. But at least until now, we have this impression that existence of the unital lift somehow may be related to amenability of the G. Okay, I will return back to this point later. But now I wanted to, before this, I wanted to say something about the proof of theorem 1. Okay, but before sketching the proof of theorem 1, I want to consider two main cases when to be a group of the main classes of the groups. The first is compact groups. When G is a compact, then there it has a Haar measure, and the existence of Haar measure helps us to introduce this lift psi. We know that already that by the assumptions of a theorem 1 that such completely positive linear lift exists, and now we have Haar measure. And we just consider this, we take some average of the theta over G by this existence of the Haar measure. But in this case, psi will be equivariant, is stronger. Okay. And then the second one is when G is an amenable group. When G, okay, here I assume that the G also is discrete, but we always have the notions of the Fulner sequences, for Fulner sets also in the non-discrete case, but just for convenience, I assume that G is a discrete group. And then, so now what we can do is that we have a lift theta from A to B that we just know that is a completely positive and linear, and we have these Fulner sequences. And now, if we have the finite set of A, compact set of G and epsilon, we can find such Fulner sequence that satisfies in this relation. And then we construct this, our favorite, our desired leaf from this leaf. and some type of the averaging over the Fourier sequence. And as you see, that's and then we have again this equivariance property of this psi. But you can see that it is strong because it does not relate it to equivariance property of phi. Okay, both in the compact group case and amenable case, we will see that we use this lift and the type of the averaging process to produce this new lift with the equivariance properties. But when we don't have any the kind of these assumptions, and we just have a general locally compact second group. So the averaging process, we have still want to do some averaging process, but here with the help of some type of the approximate identity. And this is the lemma. It helps us to do the averaging. This is the variations of some result of the Kasparov. That in the case that G is locally compact second countable, and I is be sigma unit of G invariant ideal in some G algebra, then we can find such approximate unit with this equivariance property. And now I just want to emphasize that now this approximate identity will play the role of the Fourier sequence or Harmager for us in our averaging process. Okay. But so maybe I will just first go to this slide. First, we proved the theorem 1 in a special case when the quotient is the Kalkin algebras. So I just briefly explained that if we have some G algebra, then we can get the multiplier algebra, and that these actions induce also an actions in MI, but this you do not expect that this action be continuous. So we just consider the continuous part of these actions, and I will show, but maybe I will just go a bit. No. Maybe I should. Okay, and then also we have Kalkin algebra that it is MI or mod I, and also we have another induced actions that I show it by gamma bar here, and then also this is not a continuous actions; they are just continuous with the strict topology here for MI, and so I will just consider the continuous part of them. Okay, so now the result is say that if we have a completely positive map from a linear from A to the Kalkin algebra, and we have a lift from A to by this algebra, I mean that the continuous part of MI with respect to this action, then we can find this this almost equivariant lift. Okay, so.
Sorry. Can I ask about the result that you the last inequality that you have there?
Yes.
The second one cannot be really.
Sorry, what do you mean? This second norm can? Yes, but
at the end,
yeah, but yes, but for example, in some nice cases, we should be equivariant, so it's 0.
But is equivariant, right? Because the pi is given by the lift that you have from the beginning. You don't have
No. This is not the lift. This is the original one. This is the one that you have. This in here you cannot see any. This is theta. This is theta prime. This theta is just a lift, and also we do not know anything about this equivariance property. And this phi is on our hand because this is given one. Okay, so maybe now you can see in the proof that, okay, I will return back to your point again. Okay, so now what is, as I mentioned, it's we just use the Kasparov lemma to find these approximate units, and then what we can do is this to construct a new lift with some type of the averaging process and the lift that just a lift that we know that it exists, this theta of A, and then we have this theta mka that we constructed in this way. But then the point is that this theta mk in the strict topology convergence to the completely positive contractive linear map theta m, and now this theta m is a lift for phi because of the appearance of theta here and also the properties of this approximate identity. And but the more important thing is that this approximate this equivariance property of this xn helps us to show that these theta m's we can choose our desired lift from these theta m's. And here, Joanne, as you mentioned, that we have theta here, but what is important is this equivalence properties of a delta n's. And but we are also one of the old papers of the Thompsons and the Manilov. They used this theta n, and then we need here because they are. We just need to. We just have them in the strict topology, and then because of this, we really use these Kalkin algebras. Okay. So now we prove this one for a special case, the theorem one special case of the Kalkin algebra. And now I want to explain the theorem in the general case. So as you guessed, that the idea is that for general case, we go to the some case that just is we need to find the lift for a Kalkin algebra and then return back. And this can be possible by using the Busby invariance. Okay, so it means this if we always when we have this indeed our lifting by our lifting problem, we can find that these extensions of CS algebras, and then we have this Busby invariant from A to Qi that is going to multiply algebras, and then we can construct a new CS algebra. And then, okay, then we have this equivariant diagram. And then the point is that we can find another lifting problem, but in this time it is a lifting problem from A to Qi. And then by previous propositions, we can find some lift, almost equivalent lift here. But then again, use this diagram, and we can return back and construct the desired lift for our original lifting problem. So the idea is just going using a Busby invariance and going to the Kalkin algebra and then return back. Okay, so now I will return back again to the amenability and existence of the almost unitary equivalent lift of G. Okay, but here I need again to reformulate our lifting problem in order to find an equivalence between amenability and some unit existence of the unitary lift for some type of the lifting problem. So here I will just give these definitions that if Q from A alpha to B beta be a surjective star homomorphisms between G algebras and asymptotically equivariant linear section for Q is a continuous path which is asymptotically linear, asymptotically contractive, and satisfying these two properties. that is some type, that each theta t is a leaf, and we have these equivariance properties. But I just want to emphasize this here. Each theta t is just asymptotically linear. But let's just explain that what I mean by all of them. I mean that by asymptotically linear, it means that we have this limit goes to the 0. So we just drop that each theta t is linear, but we have this asymptotic property. And also for the other, like asymptotically positive or asymptotically completely positive, we just replace this how is it, the real positivity or real linearity with this asymptotically type. Okay, and now also asymptotically unital, that this limit goes to 1. And now we have this, that if G is second countable locally compact group, then the following are equivalent, that G is amenable, and for every compact metrizable G space X, the natural quotient map admits an asymptotically equivariant linear section, which is also asymptotically unital. So in order to have these new characterizations of amenability, we need also these reformulations of the lifting problem. But now I will just briefly discuss about the proof of B to A, and then I need to again develop the theory more, and then to be able to prove A to B. Okay, but here I will use, okay, maybe I will return back again, that in order that G is amenable, one of the equivalent conditions for G to be amenable is that for every metrizable compact metrizable G space X has if we consider the C of X, then its state spaces has the G invariant state. And then the idea is that we want to construct an invariant G states for C of X for such locally compact metrizable G space X. And then by Day's theorem, it's equivalent to the amenability of the G. Okay, so now also during this proof, you will see that why we assume that the leaf should be asymptotically linear, asymptotically positive, and so on. Okay. And the idea is that we have these two projections from the C of X plus C to a C of X and to the C. And then now, by the assumptions, we are want to show that B implies A. So we can find a asymptotically unital, asymptotically equivariant linear section from C of X to C of X plus C. And also we can assume that this is self-adjoint. Now we consider the CSI algebra of the continuous bounded functions on this interval, and also C0, C0 of the 1 infinity, that contains the functions vanishing at infinity. Now we construct phi from the C of X to the CV1 infinity by using this asymptotical lift, and by this formula, that this P2, as you see, that this is this one. And now we have also the quotient map to the CB1 infinity mod C01 infinity. And now, so we can, and if we compose these maps, then we find a map with this equivariant property. But then you see that, okay, I should be a bit explanations, that as you see that indeed, we use this quotient in order to get rid of the asymptotical properties. Because if they are asymptotically, since they are asymptotically linear, then P of V is a linear. And since this is a asymptotically equivariant, P of V is a equivariant. And if since phi is asymptotically completely positive map, P of V is a positive map by going to this quotient. And so now, okay, so now we are in the CB this quotient, and I just need to find the states from the state of the DC side Jabros. And then now we have this composition. And now this composition is a self-adjoint G-invariant linear contractions into C, which takes 1 to 1. And it is also this takes 1 to 1 because again, we assume that this leaves is asymptotically unital. And with P, we make it really unital. And then also it means that X has a G-invariant Borel probability measure, and the by day factorizations, by day theorem, G is amenable. So, okay. So I will just written back here again. So, but we proved that if we have this type of the lifting property, then the G will be amenable. But now in the rest of this talk, I want to discuss A to B. And meanwhile, also I want to discuss some more another problem, that in the theorem one, we always assume that there exists a completely positive leaf, and then we construct an almost equivariant lift. But it was shown that there are a completely positive map which do not admit any lift. So what we can say when we drop these conditions from theorem one, and the answer is that an idea of to answer this is to consider such lifts that in this case there is a continuous family theta t from A to B of lifts of the phi that each of that is asymptotically linear, asymptotically completely positive, and asymptotically G equivariant. So in order to drop the conditions, the assumptions of existence of completely positive leaves, we need to replace the leaves in the theorem one with the discontinuous family of the leaves, which have this state of to become linear. They are have asymptotically linear, asymptotically completely positive, and asymptotically G equivariant. But just maybe before you mentioned, you saw that what does it mean by asymptotically linear or asymptotically completely positive map? But here asymptotically equivariance means this. But as you see that also I say that asymptotically G psi equivariant. It means that still I don't want to assume that psi to be equivariant. But then we expect to have this property. Okay. And the first theorem is that here, again, we need to consider both unital case and non-unital case. The proof of the result in this case, maybe I can say the idea is very similar to the case that I explained, but here as we have this asymptotical behavior, it needs more computations. But the idea is basically the same. We need again Kasparov lemma and some type of the averaging. But here also we have another parameter T that makes everything more complicated. And the first case was the unital case, but here we need to assume that A is not only separable, but also admitting a G invariant state. And then if this is a unital completely positive map, we can find a unital asymptotically G psi equivariant lift. For psi, okay. But as you see that here, we really need to assume that A admits a G invariant states. and because this is something that we need in order to the constructions of these site T. But the good thing is that in the non-unital case, we really do not need these as options. When we do not assume any unitality, then also we do not need to assume the G equivariant state. And we always can find such lift. But also, as you see in the previous slide, still this admitting a G invariant state is also somehow related to amenability. So now it makes sense that amenability and existence of the unital asymptotical lift are related to each other. Okay. And now we can say this theorem that that is, you can consider this as a new characterizations of amenability. We already proved from 1 to 3, and from 3 to 2 also now is immediate by this one, because if G is amenable, then every G algebra has a G invariant state, and this theorem guarantees the existence of the unital lift. So now this is now we can say that it is a new characterizations of amenability by using this type of theory. Okay, so but now in the continuations of this work with suffragette, we look at the lifting problems in the category of the groupoid dynamical systems. Maybe one of the main reasons to look at this, to start this project, was the amenability of the groupoids. And also these results, these new characterizations of amenability of the groups. You see that, okay, this amenability of groupoids is important area in the different type of the fields. But the problem is that unlike the group case, we do not have the one definitions of amenability for groupoids. And in particular, we don't know that some of them coincide with each other or not. And now the idea of this work with the suffragette is that if we can characterize some of these conditions of the amenability of the groupoids in terms of the existence of the unital asymptotically lifts for when the groupoid acts on the C-star Jabros, and if it coincides with the sum of the definitions of the amenability of groupoids, or it is just another definitions of the amenability and it's useful. So they are the aim of these projects. But so I will just very briefly explain about the groupoids. That, as you see, that a groupoid is a set of the G with this composable pair, and we have also inverse, and that we have these compatibility conditions between the products and the inverse. And especially this G0 is the all elements in the groupoid that we have this relation. And now we have, I want to emphasize that I will show the domain with S and the range with R. But the first is this: what is the definitions of the actions of the groupoid on C-star Jabros? That if G is a locally compact host of groupoid, groupoid was missed here, and the A, B as C0, G0 algebras, that G0 is this set of the units of the G. And then an action of the G is a family of the star isomorphisms from ASG to ARG. As you see that since A is a C0, G0 algebras, then it has fibers and the SG and RG are in the G0. So it's the fibers of the this is their fibers corresponding to the SG and RG. And then we have this property when G and H are composable, because unlike the groups, we have G and H that are not composable. But then the next things that we should know is about the continuous actions. And then we define the continuity in this term. It's a bit more complicated than the group case. But now, what we are working is that's at the first step that we guess that we should have such theorem. It's not completely finished, but we have a hope that we will finish it soon. Okay, but here, the first idea was that's to try to see that how much we can use the same strategy that we did it for the group case. So the first thing is that we need, again, some type of the Kasparov lemma in the groupoid case. That fortunately we have it. And but still, I wanted just to explain that there are some difficulty here, because as you remember, we have our strategy was that the first solve this lifting problem in the case of Kalkin algebra, and then from the Kalkin algebra we will go to the general case. We can do also the same things, but the main problem is that if I is a groupoid algebra, then it is a C0 G0 algebra. But we don't have that MI is a C0 G0 algebra. So we don't have any actions of the groupoid on M of I. And this is the main difficulty of this project. So still we are trying to modify the proof of the actions without going to the multiply algebra. And then we can look at this problem. And then the second step is to look at if this is correct, then which of those definitions of amenability implies the unitary lift. We look at this problem and it doesn't look easy. So even in this stage, it's not very clear that measure-wise amenability, topological amenability, or which one of them implies the existence of the lift. So this is okay. I hope that I can say more in the next time that I will give talk in this project. Okay, so thank you for listening.
Okay, so do we have questions from the audience or online? Yeah.
Could you go back to the slide where you had the three equivalent things, one of the last one being amenable? Right. So I'm just wondering if you required this splitting map from, so I'm looking at point 2, say,
Yes.
it required the splitting map from A to be in fact multiplicative, like a star homomorphism. Do you think, I'm wondering if this might give you extreme amenability of
Okay, I'm not, indeed, I'm not familiar. I heard about extreme amenability, but I never look at the definition.
One way of characterizing it is, so amenability means you have this invariant mean. If you have an invariant multiplicative mean, this is extreme amenability. So that's why I'm wondering whether demanding this multiplicativity might. I don't know.
Yes, now it's interesting because so you need to probably find is asymptotically multiplicative lift.
Right.
And then now you need to find it if this exists.
Right.
And now I just wanted to see that in the proof. Okay, now I really cannot see when we move because the proof is okay. Maybe
Fair enough.
is good because because you need just. But I think that you need to assume that. No, I think this maybe I should think because now I can say yes or cannot say no, but it's interesting because now you say that extreme, okay. Yeah, because this is the type of the G invariant state that you need here, but now you need the G invariant multiplicative one. And what is the examples of the extreme amenable?
So like the unitary group of the car algebra, for example,
Uh-huh.
with the suitable weak topology.
And there are some nice actions of them on some class of CSI algebras.
That's a good question. I'm not sure.
Yeah, because here especially we need, okay, if we can just look at the C of X, because if this extreme amenable acts on X, so acts on the C of X.
So
Maybe
definitely there
we
would
just do
be,
not need to look at this, just look at this.
yeah. So definitely there would be actions on some amenable, abelian,
Yes,
on C of X.
and- And also you can see that the similarity between these statements and the counterexample that we constructed,
Yeah, right.
because we need really C of X plus C.
Right.
Okay, so yeah, maybe we discuss later. It
Sure.
looks interesting.
Yeah.
Do we have any other questions?
So can you just tell me what did you this last thing again? You have something that's a G algebra, but then it's a multiplier algebra, isn't it? A G algebra, or something, was it?
Yes, the problem is that, okay, as you remember that we solved this problem in the group case from A to the MII. And the find and say that if it is a CPC map, then we can leave psi, this is like QI. Then we find a psi that is psi is satisfies some equivariant property. But here, even if the groupoid G acts on A, then M of I is not C0 G algebra, so we cannot say that even G can act on I, M of I. Here we don't have M of I is not a G algebra. So it doesn't make sense to talk about this result.
But it's definitely.
A G algebra, it's just this clear and turned into a G algebra, right?
Is G, yes, because for G algebra it need to be first C0 G0 algebra. And it's very rarely happens that if I is a CX algebra, M of I becomes CX algebra. Okay, there are some of the elements of them that, okay, you know what is the problem is non-degeneracy. You always can find a map from the C0 of G0 to the MI. But this is not non-degenerate. And in our first attempts, we completely we did not notice this, and we just could obtain all the results, and then when we return back, we see that, oh, but this is the problem. It's not non-degenerate, and we cannot do everything. Because if it's non-degenerate, then exactly all of our steps of the proof in the group case can be translated to groupoid case. But okay, but also it's not very nice because it was very straight generalizations. But then we noticed that it's not non-degenerate. So it doesn't make sense to talk about the actions, groupoid actions on M of I. Yes.
Any more questions?
If you start with star home instead of CPC, can you get all the leaves you have to be almost multiplicative or something?
This is almost the questions of
I mean,
Ishan.
would it be useful for some result that you have? Or...
Yes, but at least with this motivation for extreme amenability, maybe. But just the only thing that okay, but then also you need to assume that this you can find them first multiplicative lift.
Yeah.
Which one do you want to? Asymptotically
if
multiplicative?
if from A to the quotient is a star home,
Uh-huh.
can you not get
Mm.
some kind of almost multiplicativeness?
No, I think that it does. At least at the moment, I cannot see that it's related to phi. Maybe it's more related. Okay, okay, let's look at the first case that there exists a lift theta. That when then we construct this almost equivariant one. If this now here, maybe we need to assume that delta is also almost multiplicative. And I think that this case is true. But if we do not assume any lift, then in order to construct this theta t, we use the Stom selections theorem from the Banach space theory. And I need to look at this very old paper, maybe 50, 70 years old. And then I wanted to be sure this if those results gives some maps which are almost multiplicative. Because as far as I remember this, in order to just, because we don't have anything, we don't have any lift, we just want to construct theta t. And then we just use some theorem, like the selections theorem. But this is a Banach space theory, not Banach algebra. Now I really don't know. I should look, at least I know that I should look at that paper, or maybe completely different approach. Yeah, but also since I never thought that almost this multiplicative one is interesting. Also, I did not think about it. Yeah, but at least for extreme amenability, maybe there is some reasons to look at this.
Okay, thanks.
Any more questions? That's it. Okay. If not, then we'll thank Marzieh again.